Hi, everyone. Welcome to Chapter 1. So, Chapter 1 comes after Chapter P. Chapter P is kind of like a Chapter 0 because the name of the chapter is literally Basic Concepts of Algebra. It's just supposed to be a review of different properties we've talked about, like properties of exponents, factoring, stuff like that. Stuff that we will use for the entire course, and you'll use in almost any math course going forward. But what we're going to be more interested in doing is instead of looking at these kind of out in space, so to speak, expressions that don't really have much of a purpose, what we can now do is solve equations and inequalities using things that look like that. Look like those expressions that we talked about in chapter P. So what we're going to do in chapter 1 is solve a whole bunch of different types of equations. And we're going to need to solve equations to answer things and answer properties of functions when we get to chapter 2 and into chapter 3. So we're going to start with talking about linear equations where we just have equations with just a single x to the first power, nothing too crazy. And then we will extend that into quadratics in 1.3, where we now allow ourselves to have an x squared. And then we will do that in 1.5, which is in a separate file. But in 1.5, we extend it to be able to solve equations of almost any power using things that we already did in 1.1 and 1.3, and then some information in 1.2 and 1.4. What we'll do is then talk about solving inequalities, I believe in 1.6, and then in 1.7, we introduce absolute value into our equation. So lots of different types of equations. We're just going to go piece by piece. So let's get right into 1.1, linear equations in one variable. Okay, so an equation in general, an equation is just a mathematical statement saying that two expressions are equal. So we have some expression on the left-hand side, some expression on the right-hand side, and if we throw an equal sign in between them, this is now an equation, right? 7 minus 5 is just like an expression we could have talked about in chapter P. Not a whole lot we would have done with it in chapter P, but it is still just an expression. 2 is just a constant. Well, that was one of the first few things we talked about in the entire course in chapter P. So saying that these two expressions are equal is an equation. Okay, but what we're going to be interested in this section is equations in one variable. So what an equation in one variable could look like is like 7 minus 5x. So as soon as we introduce an x, which we don't, 7 minus 5 equals 2 is very concrete. But the second we introduce an x, now we don't really know what x is. We don't know what it's doing there. So what we're going to do in this section is be able to solve equations with just one variable, x to the first power. So in general, we want answers that look like x equals some constant. That's not always going to happen, but for now, for this part of the section, we will say that is what's going to happen. For us to do that, we're going to use these steps. First things first, if we have fractions, we don't like fractions. We saw how messy fractions could get in chapter P. So if given the opportunity, multiply everything by the least common denominator. In doing so, you see that all of your denominators go away, and that makes our job a lot easier. Simplify any parentheses or grouping, right? PEMDAS, stuff that we talked about, even though there isn't an E in exponents and, in linear equations, still parentheses should always come first. The fewer parentheses, the better. So taking care of parentheses when we can is definitely of interest. Then we're going to combine like terms, which we did so many times in chapter P. So we're going to combine like terms, and then our goal is to isolate the variable. So what we might have to do is if we have like 7 minus 5x, we need to get the minus 5x term by itself, minus 5 times x. So to get rid of 7 minus 5x, what we can do is subtract 7 on both sides so that the x term is all by itself on one side. Well, once that x term is by itself, what we can do is multiply or divide by the coefficient. And just like that, we will get an answer that looks like x equals some constant. As always, what I'm going to say a lot in this chapter is to check your work. So now that we have equations and things to reference, it's a lot easier to check our work, right? When we're talking about simplifying a rational expression, there isn't really a way to check your work as opposed to just doing the problem again. But now what you can do is you could take your answer, plug it in, and see if your answer holds true. So let's get right into solving equations. Let's say we have 3x plus 5 equals 14. Well, we don't have any denominators. We don't have any parentheses. So what our goal is to get x by itself. Now, think about when we do PEMDAS. PEMDAS says do multiplication and division, and then do addition and subtraction. What we're going to do is go backwards because we want x by itself. We need to go backwards. So if we have 3x plus 5 equals 14, what we can do to both sides is subtract 5. If we have plus 5, we can get rid of plus 5 by subtracting 5. But like we saw a lot in chapter P, we can't just subtract 5 on one side. We need to subtract 5 on both sides. If we apply minus 5 to both sides, as long as we stay consistent, we don't change the problem at all. So whatever you do to one side, make sure you do it to the other side as well. Okay, well, plus 5 minus 5, the whole goal was to undo plus 5. Well, you have 5 apples and you take away 5 apples, now you don't have any apples, and that was the goal. Okay, well, 14 minus 5 is 9, and now the x variable term is by itself, but it's not quite by itself. We have 3 times x. So when we had plus 5, we undid plus 5 with minus 5. Okay, and you could take a guess how we would undo 3 times x. Well, plus 5 became minus 5, 3 times x. What we're going to do is divide both sides by 3. So just like we had to subtract 5 on both sides, we also have to divide both sides by 3. We can't just do it to one side. That would really break the rules of solving equations. So we divide both sides by 3. And the reason we did that is because 3 divided by 3 is just 1. Well, we never have written 1x. So 3 divided by 3 is just 1, 1x. X equals 9 divided by 3, 3. And we like doing this. What I found a lot in my time teaching is that we don't really like dealing with just single expressions. You know, again, this out in space thing I keep saying. But the second that we're solving equations, we like this little puzzle of, okay, I subtract 5 and then I divide 3, and we get an answer that actually means something. Now, we don't need to check our work for every problem. You should check your work for every problem, but I'm not going to do it for every problem just for the sake of time. But if we want to know if x equals 3 is correct, plug x equals 3 back into the original. So if x is 3, 3 times 3 is 9. 9 plus 5 is 14. Our equation is true when x equals 3. Okay, so let's just solve a bunch of equations just like this. 7 minus 5x equals 2. Well, step 1, we need to get minus 5x by itself. Okay, well, we have minus 5x. That's what we need to get by itself first. We have this plus 7 to the left of minus 5x. How do we get rid of positive 7? We subtract 7. 7 minus 7 will go away, but we can't just subtract 7 on one side. We need to subtract 7 on both sides. Okay, 7 minus 7 goes away. That's the whole point. 2 minus 7, you have $2 and you spend 7. You are now $5 in debt. And now be very careful, because what you want to do is see minus 5 and go, oh, minus 5. Let me add 5 to both sides. But that's not what we want to do. Don't forget that this is minus 5 times x. Before, we had 7 minus 5x. This 7 was not multiplied or divided. It was being added or subtracted. So we subtracted 7. But to undo negative 5 times x, we need to divide both sides by negative 5. So again, please be very careful, because 7 minus 5x, 7 is being added, we have to subtract it. Negative 5 is being multiplied, we need to divide it. Well, negative 5 divided by negative 5 would just be 1. And same thing over here, negative 5 divided by negative 5 would be positive 1. Again, if we want proof if our answer is correct, plug x equals 1 back into the original. If x is 1, 5 times 1 is 5. 7 minus 5 is 2. Okay, so feel free to check these answers as we go. Of course, they're correct, or I wouldn't be giving a presentation on it, but it is still good practice to do because as soon as we get to somewhere around 1.5, we're really, really going to need to check our answers. Okay, negative 10x minus 12 equals 0. Okay, so we need to get x by itself. We see negative 10x minus 12. How do we undo minus 12? Well, in the last few examples, we had 7 minus 5x. Positive 7, we had to subtract 7 on both sides. But negative 10x minus 12, well, if we have minus 12, the undoing of minus 12 would be adding 12. But again, adding 12 to both sides. Okay, negative 12 and 12 go away. 0 plus 12 is just 12. And same thing, we have negative 10 times x. How do we undo negative 10 times x? We divide both sides by negative 10. Okay, negative 10 divided by negative 10 is just positive 1. That's the whole point, right? We just want to get x. It doesn't make sense to divide by 5. We would be left with negative 2x. 12 divided by negative 10, simplifying fractions. We've done that before. Okay, let's keep going. 2/3 x minus 3 equals 7. Okay, well, we have 2/3 times x minus 3. Well, we need to get rid of minus 3 to get the 2/3 x by itself first. How do we undo minus 3? We undo minus 3 by adding 3 to both sides. Minus 3 plus 3 is nothing. 7 plus 3 is 10. And now we run into a slight problem because all the other ones that we've had to divide by, we would divide by like 5 or negative 10. But now we have 2/3 and we would want to divide by 2/3. But don't forget that dividing by fractions is like keep, change, flip. And we kind of saw that keep, change, flip can be a lot of work sometimes. Instead, let's jump right to a better, more efficient way of thinking about this. When we divide by 2/3, keep, change, flip would say multiply by 3/2, right? Keep whatever we're multiplying by, or keep whatever we're multiplying, change the sign to multiplication, and flip the thing that you are dividing by. Okay, well, if we're dividing by 2/3, that would be the same as multiplying 3/2, right? Keep, change, flip. So a more efficient way of thinking about this is when we have a fraction on one side, why don't we multiply both sides by the reciprocal? The reciprocal of 2/3 is 3/2. But again, can't just multiply 3/2 on one side, need to multiply it on both sides. Okay, don't forget fraction multiplication. 3/2 times 10. 10 is the same as 10/1. Don't do 3 times 10 and don't do 2 times 10. 10 is 10/1. Okay, well, over here, 3/2 times 2/3. 3 times 2 is 6. 2 times 3 is 6. 3 times 10 is 30. 2 times 1 is 2. So we multiplied by the reciprocal because we now get 6/6. And we know that 6/6 is just 1. The same thing happened, right? We wanted to get a 1x, and we got it by multiplying by the reciprocal. You could still divide by 2/3, but don't forget that when you divide by 2/3, that's keep, change, flip. You just got to be a little bit more careful. So multiplying by the reciprocal, just as equally correct. If anything, it's more efficient. Well, 30/2 is 15. 6/6 is 1. So our final answer is 15. Okay. I'll also take the second to note that if you can solve these problems faster than how I'm doing them here, that's totally fine. I'm teaching this with showing all the little pieces of what's really happening. I don't really expect anybody to actually show the step of multiplying by, of adding 3 to both sides. What you're more likely to do is jump from this line down to this line, and that's totally okay. Like I said, I'm just showing what happens in those steps. Okay, Let's continue. 3 times 2 minus x plus 4x equals 3x. Well, PEMDAS, take care of parentheses first. So why don't we distribute 3? 3 times 2 is 6. 3 times negative x, negative 3x. Okay, well, we have multiple x's on one side, so why don't we combine like terms? Negative 3x plus 4x. If I am $3 in debt and I'm given $4, now I have $1. Well, we have an x here and 3 x's over here, so why don't we bring all the x's to one side? Well, we like to have our constant be away from the x's, so what I'm going to choose to do is subtract x on both sides. How do I undo plus x? By subtracting x on both sides. Plus x minus x just goes away. You have 3 apples and you eat one of them. Now you have 2 apples, and then we just divide both sides by 2. Okay, so fear not. It's okay to have 3 equals x. Just because it's not x equals 3 doesn't mean anything went wrong. 3 equals x, same thing as x equals 3. And now this is a really good opportunity to tell you, you always have a choice of where you bring your x. I think a lot of people prefer having x on the left-hand side. So what you could have done here as well is subtract 3x on both sides and subtract 6 on both sides so that all the x's were to the left and your constant was to the right. You would get the exact same answer. It functions the exact same way. However, whichever one is more comfortable for you, by all means, go for it. Okay, let's do another ugly one with a lot of parentheses. Well, we got a parentheses inside a bracket, right? Brackets are just another way of writing parentheses. So why don't we distribute -2 first? -2 times x is -2x. -2 times -2 is +4. Okay, well, before we do anything else with this, with this minus on the outside, why don't we simplify our inside? 3x minus 2x. 3 apples minus 2 apples, 1 apple. Okay, well, nothing else we can do inside the brackets, so why don't we distribute our negative sign and combine like terms? 6x minus x is 5x. Okay, and now we're just back to an equation we've been solving. Alrighty, let's add 4 to both sides, and let's divide both sides by 5 to get x equals 3. Not so scary. Could always be worse, and it does get worse, but it's not so bad for right now. Well, let's do one more example, and I told you if you have a denominator, multiply by the LCD, and here's why. Well, what you could do is 2x over 9 plus 1 over 9 minus x over 6 minus 4 over 6. That's a lot of fractions, and we saw how much work just simply adding and subtracting fractions took. So instead of trying to deal with multiple fraction, addition, and subtraction, why don't we multiply everything by the least common denominator? Okay, what is the least common multiple of 9 and 6? What's the first multiple that they share? The answer would be 18. So what we're going to do is multiply everything by 18. Okay, literally multiply everything by 18. Okay, well, what we're going to do is distribute 18 to each of these two fractions. 18 times this fraction minus 18 times that fraction. This is like 18 over 1, so fraction multiplication. But notice now, we have 18 times something divided by 9. 18 times something divided by 6. Well, we learned in one of the very first few sections that we can simplify 18 over 9, and we can simplify 18 over 6. 18 over 9 is 2. 18 over 6 is 3. And now from here, not nearly as scary as it initially looked with fractions. Let's distribute 2. Let's distribute -3. We can combine some like terms. 4x minus 3x is just x. +2 minus 12, you have $2. You spend $12, you are now $10 in debt. And last but not least, we only need to add 10 to both sides. Don't even need to divide everything by some number because x is all by itself. So that's solving linear equations. Not as scary. If it sounds like I overcomplicated it, but you can get the same answers, by all means, do it your way. It's totally fine. I'm just showing you what's really happening on the inside for a college math class as opposed to, high school taking things for granted. Okay, so, well, those aren't the only types of equations we can get. We can get other, like, weird looking equations. So, what we had are conditional linear equations. Conditional linear equations just say that there's only one solution. When x equals 3, this equation is true. But that doesn't always happen. We have an infinite number of options for what we put on both sides. So we introduce two more types of equations. First one is an identity. An identity is any equation where the solution is all real numbers. Or in other words, no matter what you plug in for x, you will always get an equation that is true. And you'll see how that looks when we do an example in just a moment. We can also say infinitely many solutions, right? If we're talking about solutions, conditional only has one solution, but all real numbers would mean we have an infinite number of solutions. Likewise, we have an inconsistent equation, and an inconsistent equation is an equation with no solution. It means that no matter what we plug in for x, we can never get an equation that is true. So let's just do some examples and see where it takes us. They don't look any different from other equations, so you can't really think like, oh, this one's going to be an identity. We don't know. You'll see kind of quickly like warning signs of how these things would happen, but in other words, just solve them like any other equation. Well, we got a bunch of parentheses, so why don't we distribute this 2, and why don't we distribute this negative sign? Okay, we have some combining like terms we can do, minus 12 plus 5, and 12 minus 19. And now maybe here you already start to see something kind of weird. Okay, why don't we add 7 to both sides? And why don't we subtract 6x on both sides? We could divide both sides by 6. We get x equals x, but we still need to combine those x's. So let's bring all of our x's to one side by subtracting this 6x on both sides. However, when we subtract 6x minus itself on both sides, we get 0 equals 0. So your indicator that your equation is an identity is that you end up, after simplification, you end up with a statement that is always true. 0 equals 0 is always true. There is never a time that 0 doesn't equal 0. So what we got is something that says no matter what we plug in for x, we will always get the same value on both sides. Don't believe me? Plug in anything you want. Let's just plug in 0 to say, I don't know. 3 times 0 is 0. 0 minus 6 is negative 6. 2 times negative 6 is negative 12. Negative 12 plus 5 is negative 7. Okay, so our left side is negative 7 when x equals 0. All right, well, when x equals 0, 6 times 0 is just 0. 19 minus 0 is 19. 12 minus 19 is also negative 7. Well, what if x equals 2? I don't know, let's do something else, right? When x equals 2, 3 times 2 is 6. 6 minus 6 is 0. 2 times 0 is 0. 0 plus 5 is 5. When x equals 2, 6 times 2 is 12. 19 minus 12 is 7. 12 minus 7 is also 5. So we had two different answers, x equals 0 and x equals 2, that when we plug them back in, we get the exact same thing on both sides. So no matter what we plug in for x, we always get the same value on both sides. That's to say we have an infinite number of solutions. This equation is an identity. Okay, well, let's see what the opposite would look like. All right, lots of parentheses. Let's take care of this innermost one. Let's distribute 2. Let's combine like terms 3x plus 2x. And let's distribute this negative sign to 5x and negative 2. Well, we can combine like terms and say 5x minus 5x is, oh, that goes away. And we get 2 equals 1. However, 0 equals 0 is always true. But you're probably a little confused now because we're saying 2 equals 1. But 2 doesn't equal 1. 2 never equals 1. So what we got is the opposite, so to speak, of an identity. We got an inconsistent equation. We got an equation that no matter what we plug in for x, we will never get the same value on both sides. We will always end up at an equation that is never true. So in that case, we say there is no solution. Okay, well, a little bit short of an explanation because we went through all the explanation for an identity, and inconsistent is just the opposite. If we get an equation that after simplification, after solving, is always true, it's an identity, infinitely many solutions. If we get to a simplified equation that is never true, like 2 equals 1, that's never true. That's inconsistent. It has no solution. Let's do another 2 examples to see what happens. All right, lots of parentheses. Let's distribute 2. Let's distribute 5. Minus 5x plus 2x and 1 plus 14. 2x minus 5x, lots of combining like terms. Maybe you already start to see something happening. Okay, let's subtract 15 on both sides, and let's add 3x to both sides. Right? We want to get all the x's to one side, so we need to add 3x to both sides. And we again get 0 equals 0. That is always true. No matter what we plug in, both sides will always be equal, infinitely many solutions. Don't believe me? Take any x value you want, plug it into the original equation, and you will see both sides are always equal. Okay, another one. Again, lots of parentheses. Let's distribute -6. Let's combine like terms. Let's distribute this negative sign. Let's again combine like terms. 3x plus 4x is 7x. Let's subtract 7x on both sides. And when we do that, 7x goes away on both sides, and we get 6 equals -1. And we are well aware that 6 does not equal -1. So we got to an equation that is never true, no solution. Okay. As a nice little summary, again, identity, the answer is always true, like 0 equals 0. So if you get 0 equals 0, 2 equals 2, -5 equals -5, that equation is an identity. It has an infinite number of solutions. Inconsistent, the answer is never true. It's like 2 equals 1. So if you get an equation and you solve it and it gets to something like 2 equals 1, -5 equals 3, whatever it is that doesn't make any sense, your equation is inconsistent. And conditional, there's only ever one answer, like x equals 3 or x equals -1, but we don't typically need to say conditional. Conditional is taken for granted. When we come to an identity, it's important to us that we can recognize an identity equation. It's important to us that we can recognize inconsistent. But when it comes to conditional, it's not as important to say it's conditional because we're just more interested in what is the answer, right? There isn't a concrete answer for 0 equals 0 or 2 equals 1 outside of infinitely many solutions or no solution. So in conditional equations, you don't need to say conditional. All I want is the answer. And in most cases, all your instructor would want is just what the answer is. Okay. And that brings us to formulas, or more specifically formulae, but for the purpose of what we're going to talk about, let's use formulas. Okay, so this is right here for you. But formulas in general are equations that show relationships between two or more variables. So what we've done so far is in a linear equation in one variable, but we know that almost any formula on the planet has more than one variable attached to it. So if we wanted to show a relationship between multiple variables at once, that is called a formula. So some examples: Celsius to Fahrenheit, Fahrenheit equals 9/5 Celsius plus 32. Volume, length times width times height. So just as an example, right, a relationship between two or more variables. Here, there's two variables, Fahrenheit and Celsius. So this would be a formula. Volume equals length times width times height. Well, that's four variables, so that is also a formula. So if we wanted to find out what 15 degrees Celsius is in Fahrenheit, what we can do is plug in 15 for Celsius, right? We want 15 degrees Celsius. We want to find it out in Fahrenheit. So let's plug in 15 for C. Okay, 15 over 5 is 3 over 1. 9 times 3 is 27. 27 plus 32 is 59. So 15 degrees Celsius is 59 degrees Fahrenheit. Okay, but we just did Celsius to Fahrenheit, and how would we go from Fahrenheit back to Celsius? Well, one option we have is to just plug in what Fahrenheit is and solve for C. However, that's not the most efficient. If I asked you, what is 20 degrees Fahrenheit in Celsius? And then I asked you, what's 40 degrees Fahrenheit in Celsius? And then 60 degrees Fahrenheit in Celsius, and then 80 degrees Fahrenheit in Celsius. Are you going to continuously plug in 20 and then solve for C, and then plug in 40 and then solve for C, and then 60 and solve for C, and so on? No, that's kind of inefficient. We would like to save ourselves some time. So a better method, a more efficient method, would be to solve for C first and then plug in Fahrenheit. So this is called solving for variables. Let's do an example of this. So let's solve the Fahrenheit to Celsius equation for Celsius. Well, what we're going to do is, even though we have two variables here, we want to solve for C. So treat everything else as a number. Okay, so Fahrenheit, I understand that that's a variable, but let's just treat it like it's a number. Maybe not a number that we can combine, but let's just treat it like a number for right now. Well, if we wanted to get C by itself, you would start by subtracting 32 on both sides. And then to get rid of 9/5, we would multiply by the reciprocal, 5/9. Well, 5/9 and 9/5, 45 over 45, that cancels out. Oh, and just like that, we've derived the formula for Fahrenheit to Celsius. So now, if I asked you what multiple degree Fahrenheits are in terms of Celsius, this is so much easier. Now you could just plug 20 into here and simplify, 40 into here, 60, 80, instead of needing to plug in 20 into here, and then 40 into here, and then 60 into here, and 80 into here, and continuously having to solve for C that way. So there is a huge benefit for us to solve for variables first, and that's not just for math, that's for anything. You might see in some of your biology classes or chemistry classes or physics classes that if you have to do multiple calculations of the same thing, maybe solving for the variable first can save you some time later. Okay, so one more example of this. Let's solve for the variable h. Well, we have an h here. We have an h here. If you're unfamiliar with this formula, this is the surface area for a rectangular prism, so a surface area of a box. But let's solve for h, which means if we're solving for h, treat everything else like a number. Maybe not a number that you can simplify, but a number nonetheless. Okay, think back to when we were solving equations with just x's. We wanted all the x's on one side. So if we're solving for h, let's get all of our h's on one side and all of our non-h's to the other side. Okay, well, we have an h here, but 2 length width does not have an h in it. So let's subtract that on both sides. Let's get that out of there. Now, not super obvious how we would combine 2 length height plus 2 width height, but what we do notice is that they both have an h in common. Well, think back to P4. If they both have an h, we can factor out h. Okay, last but not least, we have h times 2 length plus 2 width. Well, think back to when we were doing this for normal equations. If we had 6 times x, we would divide both sides by 6. Here we have h times something. How do we get rid of h times something? We divide both sides by that something. So 2L plus 2W over 2L plus 2W, those factors cancel out, and we're left with just this ugly looking formula for H. So maybe not so often that you would be, given the surface area and not the height, but just good practice for solving for variables. So that's the end of P1. So P1, like I said, just linear equations in one variable. I understand that this might have sounded a little complicated. Again, however you solved for equations in one variable in the past, whatever's easy for you, shortcuts you might use, they're all still correct. If you get the same answer and your work is just a little different, there's no way you can cheese these answers, right? Maybe some of them a little easier than others, but there's no way you can get to the right answer by doing the wrong work in most situations. So, like I said, too complicated. I get it. I'm just trying to explain it in as much depth as I can for a course of this level. So that's the end of 1.1. In the next section, 1.2, we're just going to do some applications of linear equations. Not a whole lot, just kind of like an exploration of some things. So yeah, I'll see you in 1.2. Bye.
Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Leswowska Zerpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.